In this video, I'm going to be talking about the existence of a derivative. If a function is continuous on a closed interval between 2 points, then the function is differentiable on that open interval between those 2 points. So it's not differentiable at the endpoints where the function is continuous. If a function is differentiable, then that must imply that the function is continuous. And if a function is continuous, that implies that the function has a limit. The converse of this is not true, and this is where they try and trip you up on AP tests. If the limit exists at a certain point, that does not necessarily mean that the function is continuous at that point. It could be a hole, in which case the limit would exist but not be continuous. And just because a function is continuous does not mean that the function is differentiable at that point. And we'll talk about examples of why. When does a derivative not exist? Well, it can't exist if there are discontinuities at that point. For example, here we have a hole. It could be defined elsewhere or not defined at that point. It is not differentiable at that point A. Even though the function has a limit, it is not continuous, and therefore it is not differentiable. In this example, a different type of discontinuity, a jump, or non-removable discontinuity. So again, at x equals 1, I can't find a derivative at that value. Remember, a derivative means slope. So if I can't even find the slope of the line at that point, I must not be able to find the derivative. So here the function does not even have a limit and is not continuous at 1, and therefore it does not have a derivative. Infinite discontinuities is another spot where we can't find the derivative of the slope of a function. And also oscillating discontinuities happen a lot in trig functions. We also cannot find the derivative inside that mess. So again, if a derivative exists, then it automatically implies that the function is continuous and has a limit at that spot. But we can't think about that backwards. It's always got to be top down, starting with the derivative. Another example of where we can't find a derivative is at a sharp point called a cusp. And the reason being is that I can find the slope just to the left of that. I can find the slope just to the right of that. But exactly at that sharp point, I don't know whether my function is increasing or decreasing. I don't know what the slope is. Therefore, I cannot effectively evaluate the derivative at that point. So even though this function is continuous, even though the limit exists, it's not differentiable. Absolute value functions are a famous example of this. Here we have our absolute value function. It's a V form. When values are less than 0, I have a negative slope or a decreasing line. When values or x values are greater than 0, I have a positive slope. So I can find the slope everywhere except right here at this sharp point. And if you find the derivative of the absolute value graph, that would be the slope of this line. That would be -1. So I have a constant function for my slope or my derivative. And over here, the slope of this part of my absolute value function is +1. So I can find the slope or the derivative function, which is just a constant horizontal line at 1, +1. But right there at that sharp point, I am unable to evaluate the derivative. I can't find the slope. That's why we have open dots on our derivative graph. And I can't find the derivative at the sharp point. One last case is that we can't find derivatives at vertical tangent lines. The reason why we can't find derivatives at vertical tangent lines is because of this thing called a change in concavity. So this graph is facing up right here along this interval. And then right here, it switches and changes to facing down. And that's known as concave up and concave down. And so right there at that vertical tangent line, it switches or changes concavity. And so we actually can't find the derivative at that spot. And the reason why is because if we derive this function, for example, this is a cube root function. Here's its most basic form. And if I find the derivative of that function, I get this. And if I plug in 0 into this function, I get an undefined value. And if I graph this function, I actually get this function, which has a vertical asymptote at 0. And so we can't find derivatives at that infinite discontinuity. And so the reason is that the vertical tangent line, that change in concavity, turns into a vertical asymptote when you find the derivative of a function, and we can't find the derivative at that point. So 3 cases where we can't find derivatives: vertical tangent lines, sharp points or cusps, and any discontinuity type. And one more time, if the derivative exists at a certain point, automatically implies that the function is continuous at that point and that the limit exists at that point. Not true if we try and describe that backwards. Just because a limit exists does not mean it's continuous at that point, and just because a function is continuous at a point does not mean that the derivative exists.